Hello, good morning everyone. This is Dr. Foram M. Joshi from GSET, and we will continue with our lecture of Chapter 2 or Unit 2 of our new physics syllabus. The course code is 2110011 and we will be moving ahead with the magnetic materials. We have also discussed the initial topics from this magnetic materials, the origin of magnetism, definitions and definitions of magnetic moment, magnetic dipole, magnetic field strength, magnetic flux density, intensity of magnetization, magnetic dipole moment, and another definitions related to that, magnetic field intensity, magnetic susceptibility, permeability, etc. We also had a glimpse of classification of magnetic materials on the basis of their magnetic moment, the orientation of their magnetic moment. We have classified the materials in 5 major types: diamagnetic materials, paramagnetic materials, then ferromagnetic materials, anti-ferromagnetic materials, and ferrimagnetic materials. Today we are going to do some of the numericals which are related to these definitions, and then we will move ahead with the another syllabus topics, right? So we will move to the tabletop for the examples. We are given the data in terms of several magnetic quantities. We are given initially in the first example that H is equal to, that is the magnetic field intensity of a paramagnetic material, is H, which is 10 raised to 4 ampere per meter, right? And its susceptibility at room temperature is, as you can see, it is 3.7 into 10 raised to minus 3. We are asked to find out what is the magnetization. For this we will use the simplest equation for chi, that is chi is equal to m by h. This is actually the symbol for the susceptibility. Chi is equal to m by h. That implies that m is equal to h into chi. And if I substitute the values, H is 10 raised to 4 ampere per meter, and chi is 3.7 into 10 raised to minus 3. So the answer is 37 ampere per meter. Since magnetization's unit is ampere per meter, don't forget to write down the unit. Okay, now we will move ahead for the second example. The second numerical is a bit different. It gives us the magnetic field strength. Magnetic field strength is, we will have to find out B, we will have to find out M, and we are given that H is equal to 2 into 10 raised to 5 ampere per meter, and mu R is equal to 1.01. What is mu R? It is actually the relative permeability, right? The relative permeability of the given material is 1.01. So which formula we should use for B? We can use for B is equal to mu H. As you can see that capital B can be found with the use of the permeability. Mu is equal to, again mu is equal to mu 0 into mu R, because mu is the absolute permeability, mu 0 is the permeability of the vacuum, and mu R is the relative permeability. We can have this formula for the finding of B. This is 4 into 3.14 into 10 raised to minus 7 into 1.01, which is the relative permeability, into 2 into 10 raised to 5. So we can have as an answer 0.2537 Weber per meter square. For the second part of this equation, we should find out M is equal to what? M is equal to, in order to find out the magnetization, we can use another equation of chi. Chi is equal to mu R minus 1. We are given that mu R is 1.01 and this is 1. But again, we have used the equation in the first example. Chi is equal to m by h, and we are given h. So capital M is equal to h into 0.1, right? What is h? 2 into 10 raised to 5 into 0.1, sorry, 0.01. So the answer is 2000. What is the unit? Unit is ampere per meter. So capital M, that is magnetization, is 2000 ampere per meter. Okay, we can go for the another example, that is again it is a paramagnetic material. It has a BCC structure. Paramagnetic material having BCC structure with a cubic edge small a is equal to 2.5 angstrom. What do you mean by angstrom? It is 2.5 into 10 raised to minus 10 meter, right? Since it is a BCC structure, all the three edges have same value of 2.5 angstrom. We are given that if the saturation value of the magnetization is 1.8 into 10 raised to 6 ampere per meter. Saturation value of the magnetization is 1.8 into 10 raised to 6 ampere per meter. Then we will have to find out the average magnetization contributed per atom. What do you mean by this? We discussed the Bohr magneton, right? Now number of atoms per unit volume. What is the value of this for BCC? Per unit volume. What is the equation for this? You may have studied earlier that it is the number of atoms in the unit cell divided by the volume of the unit cell. That is, this is equal to a cube, and small n value for BCC structure is 2. So what will be the answer? 2 divided by a cube, that is 2 divided by 2.5 into 10 raised to minus 10 raised to 3. The answer is 1.28 into 10 raised to 29 atoms per meter cube. This is actually number of atoms per unit volume. Okay. Now what is the average magnetization produced per atom? If I denote that by m dash, then what will I get? M dash is equal to total magnetization divided by the number of atoms in any of the material. Here we have got the answer, the number of atoms per unit volume, and we have also the value of capital M, 1.86 into 10 raised to 6 divided by 1.28 into 10 raised to 29. What is the answer? What is the division? 1.406 into 10 raised to minus 23 ampere per meter square. Right. Now what is Bohr magneton? Bohr magneton is the smallest unit of magnetization. The equation says that it is EH into 4 pi m. What is E? E is the electron charge, H is the Planck's constant, and in the denominator 4 pi small m is the charge of the small m is the mass of the electron. So putting this constant, what we can get? The value of this is 9.27 or say 9.274 into 10 raised to minus 24 ampere per meter square. So the quantity that we have to find out, the average magnetization per atom in the unit of mu b is what? M dash divided by mu b. What is m dash? We have found 1.406 into 10 raised to minus 3 divided by 9.274 into 10 raised to minus 24. The answer is, sorry, here it is 23. The answer is 1.5163 Bohr magneton or mu b. In terms of mu b, the average magnetization produced per atom is 1.5163 Bohr magneton. Okay. So we can move ahead with the another example. This numerical says that 2 point it says that the saturation magnetic induction of nickel, that is Bs, the saturation magnetic induction of nickel is 0.65 Weber per meter square, while the rho, the density of the nickel, is 8906 kg per meter cube. What is the atomic weight of nickel? The atomic weight of nickel is 58.7. And what we have to find out? We will have to find out the magnetic moment of the nickel atom in Bohr magneton. That is our question. In terms of Bohr magneton, we will have to find out. Okay. Now we know that Bs is equal to n mu 0 mu m. That means mu m, the magnetic moment, is Bs upon n mu 0. Okay. So also capital N is what? It is the number of atoms per meter cube in 1 kg of substance. So N can be found with this formula, rho Na divided by atomic weight. So how can I find out this capital N? It is 8906 multiplied with Avogadro number. What is the value of the Avogadro number? Yes, 6.023 into 10 raised to 26, and it is divided by atomic weight of nickel, that is 58.7. So capital N is equal to 9.138 into 10 raised to 28 atoms per meter cube. Using this capital N, we can find out the mu m. Mu m says that according to the equation, it is Bs is 0.65, Bs divided by n mu 0. So it is 9.138 into 10 raised to 28 multiplied by, that is mu 0, 4 into 3.14 into 10 raised to minus 7, right? That is 4 pi into 10 raised to minus 7, the permeability of the vacuum. This is 5.6632 into 10 raised to minus 24 ampere meter square. This is actually the mu m in terms of ampere into meter square. But what will you do for this to find out the mu m dash, that is the magnetic moment in terms of the Bohr magneton? It is 5.6632 divided by, say, into 10 raised to minus 24 divided by the standard value of mu b, 9.27 into 10 raised to minus 24. That the answer is, what is the answer? What is the answer in terms of Bohr magneton is 0.6109 mu b, right? So this is the answer in terms of Bohr magneton, that is the magnetic moment of the nickel is 0.6109 Bohr magneton. We can move ahead with the another example. We can say that we are given that the silicon material is subjected to a magnetic field of strength 1000 ampere per meter, and if the magnetic susceptibility of silicon is chi of silicon is given as minus 0.3 into 10 raised to minus 5, then calculate its magnetization. We will have to calculate the magnetization, as well as we will also calculate the the magnetic flux density. Which formula? Again the formula is repeated. Chi is equal to m by h. So m is equal to chi into h. Chi is minus 0.3 into 10 raised to minus 5. into again H is 1000. So it is minus 3 into 10 raised to minus 3 ampere per meter. While for B, there is another formula. It is mu 0 H plus M. Mu 0 is what? It is again 4 pi into 10 raised to minus 7 H plus M. What is the answer? 3 into 4 into 3.14 into 10 raised to minus 7. What is H? H is 1000 minus 3 into 10 raised to minus 3. So what is the answer? What do you mean by the answer sheet? That is 1.256 into 10 raised to minus 7, 10 raised to minus 6, and this is given by 999.997. The multiplication gives the value of B as 1.2559 into 10 raised to minus 3 Weber per meter square. Right? So we have found B and we have also found M as minus 3 into 10 raised to minus 3 ampere per meter. These are the two answers. Those were required in the example. Now the last numerical that we can do here is in that we are given the magnetic material. The magnetic material has a magnetization of 3400 ampere per meter. We are given M. M is equal to 3400 ampere per meter inverse. And the flux density of 0.0048 Weber per meter square. This is the magnetic flux density B. Now calculate the magnetic field, the applied magnetic field and the relative permeability of the material. These are the two quantities that we will have to find out. Now how can we find out? See, we have a well-known formula, chi is equal to M by H. M is 3400 divided by